In this tutorial, we'll be using a RayTK scene to control geometry instancing using volumetric sampling. We will be using RayTK version 0.14, so make sure you're using at least that version. There is a download link in the description. There is also a link to download a project file with the completed scene. I'm going to start by dropping the toolkit talks into your project. Next, we're going to use the Alt-R shortcut to open the RayTK palette. And we're going to create a Raymarch render 3D. And we're going to add a null top connected to the first output. And this renderer is going to be used for previewing our scene, but it's not the actual volumetric part of it. We will get to that in a little bit. I've set up some panels on the side here to display the different rendering output. If you want to see how this is done, you can take a look at the project file download. The geometry that we're going to be using for this scene is going to be relatively simple, since that isn't really the main focus of the tutorial. I'm going to use the Alt-R shortcut again to open the palette and create a torus SDF. Then we're going to connect that to the first input on the renderer. And you can see that the output of that renderer is being displayed in this side panel here. So going back to the torus SDF, we're going to change the axis parameter to be Z. That way it's facing the camera. And we're going to change the radius to 1 and the thickness to 0.5. And I'm going to change the resolution here to fit that shape a little bit better. Just going to use 2000 by 2000 so it fits in the square pane. Next, we're going to create a mirror octant and insert that between the torus and the renderer. I'm going to set the X and Y size to 0.5 and set the Y offset to 0.5. Next, we're going to add some animation to this rotate axis parameter to get it some motion that we can use to show how things are working later on in the scene. To do that, you can use a simple expression like abstime.seconds and multiply that by some number. Since remember this rotate is in degrees, so it's a 0 to 360 range there, so you would want to multiply that. Alternatively, you could use chops, which are going to give us a little bit more control, so I'm going to get rid of that and create a constant chop. Going to set the channel name to rotate and set the value to 0.2. Add a speed chop connected to that constant. And add a null to the end. So you can use the Alt-N shortcut to do that. And remember, since we are dealing with degrees of rotation, you're going to need larger numbers than this. So you can either change the number in here to something large, or you could add a math chop to multiply it. I prefer using math chop because it lets you use this slider without having to go outside that 0 to 1 range. I'm going to move this over a little bit and insert a math chop between those, and on the multiply setting, I'm going to change that to 60. Now I'm going to take the channel that we've just created, drag it onto the mirror octant and onto the rotate axis parameter, and choose chop reference. We've now got some animation there, and we can move on to the next steps in the scene. Now, what we've created so far is a standard Raymarching setup. We have some operators here that are defining a signed distance function, which is basically a shape, and then we have a Raymarch render 3D here, which is using that and using the Raymarching process to use it to produce an image. These other parts of the scene here don't really even have anything to do directly with Raymarching. They're basically just the definition of a shape, and it's Raymarching because that's how this one renderer uses it. For each pixel in the output, it figures out what direction a ray of light would be moving from a camera position into the scene. So you've got your camera position here, and your screen is essentially like a little rectangle there, and for each pixel it figures out what direction it goes in, and then it does a series of these steps, and this is where the term marching comes from. So at each one it looks and sees what is the closest surface. So here it's this point down here, and how far away is it, and so it uses the SDF to figure out that distance, and it knows that it can go at least that far without hitting anything. And it keeps doing that until it gets so close to a surface that it says that it has hit that surface. So the details of this aren't important to this, but just the idea that the renderer is going through this series of steps, and at each one of these points, it's kind of asking the scene, what's the closest shape? And there is a link in the description to the tutorial that this comes from. I recommend reading it if you're interested in the kind of theory of Raymarching. As we said before, the reason that this is a Raymarching scene is because this particular renderer is using the scene to do Raymarching. But there are a number of other types of renderers that use the scene in different ways to produce other kinds of images or data. The point map renderer, which we're going to create one of those, open the palette, create a point map renderer. We're going to place that up here. And this renderer is similar to the Raymarch renderer in that it takes in this scene definition in the first input here, and it uses that to produce images. But the way that it does this is very different from how the Raymarch renderer does it. Instead of going through this process where it's kind of moving this point along in space, all it does is ask, and it takes in a top that contains coordinates. So each pixel would be red as X, green as Y, blue as Z. For each pixel in the output, it asks the scene about that point in space and then produces output based on that. So it's really only kind of asking that question of the scene once per pixel, which ends up being a lot more efficient because just the work that it needs to do is a lot simpler. I'm now going to insert a null dot in between that scene, the scene operators in the renderer here, so we can more easily connect this to both of them, and we can kind of swap things out there later more easily. Going back to our point map render and create two null tops coming out of this to the two different outputs. For the output that has the label SDF or value, we're going to name the one connected to that SDF data. And the other one that's color, I'm going to call this color data. Now the ordering of these two outputs has changed in this release of the toolkit, so just make sure you're paying attention to what the label is when you mouse over and make sure you're connecting them to the right thing. Now right now, both of these are showing up as empty. It's because it doesn't have any coordinates to work with. So in order to get this to work, we need to give it those coordinates. We're going to start with using a SOP geometry to create the points. First, create a box SOP. Going to switch on the division setting here and set all of those to 20. Going to set the scale of that to 2. And if you open this up, you can see that it gives you a three-dimensional grid of points going from -1 to +1 on all three axes. Next, we're going to create a SOP to chop to convert all those points into a set of channels. Next, we're going to create a chop to top, which is going to convert those into a set of pixels. Now, if you middle mouse click on this, it's producing a top that is 9,261 pixels wide by 3 pixels high. So it's 3 pixels high because right now the data format is red. So it's using a separate row of pixels for each of these 3 channels. What we want instead is to go with RGB. So if you middle mouse on this again, now see that it is just a single row of pixels. And it's using those channels as the red, green, and blue for each of those pixels. It's laid out in a single very long line, and that can be okay, but it can sometimes be hard to work with. If you want to, say, open up a viewer to look at this, viewing it as a single line gets a little bit harder, and it's a little bit less efficient for the GPU. To change that, this image layout setting, you can use fit to square. So it will create a square that is large enough to fit all of those pixels. And if you open this up and take a look inside, you can see that it's got all these pixels here, and then there's this dark area at the top. And these are pixels that didn't actually exist. They're just filler to make it fit a square. Now right now, there isn't anything in the data itself that would tell us which ones are just black because their coordinates are 0, 0, 0, and ones that are black because they're not real points. So what we want to do is use the alpha channel to represent whether this is a real point. To do that, in the chop to top, I'm going to change the pixel format here to 32-bit float RGBA. So it's adding an alpha channel. And in the viewer here, it's kind of hard to see because it doesn't actually show the background checkers in these pop-up viewers. But if you turn on display pixel values, you can look at all those different values here. All of those have this alpha of 1, and then you go up to those, and those have alpha of 0. So the renderer is going to know that those aren't real points. Now another thing that you can do to view this that was added in recent Touch Designer builds, in the 2021 builds, is an option to view this as point data. So there's this view as points option that you can get to right-clicking in a top viewer, and it will show it as though it were SOP geometry, which is really useful for just kind of preview purposes and understanding what's in there in cases where the data isn't really supposed to be an image, it's just data that happens to be in a top. I'm going to go back to view as image. Now I'm going to create a null top at the end here. We're going to name this positions. And I'm going to give that a separate color here just to indicate that it is an important piece of data that's going to be used in several different places. Now that we have our point data in a top, we're going to use those points to instance some geometry in a traditional Touch Designer render setup. If you have a preferred technique for instancing with tops, feel free to use that instead. But a real simple way to do this is using the Touch Designer palette, and under point clouds, there's this point render component. And drag one of those in here, close the palette, and move that over to the end here. Going to create a select top and rename this to cell or select positions, and then drag the positions onto that and connect it to the first input on the point render. You could also connect that top directly if you want, but this will help keep the network a little bit neater. I'm going to set this second panel to show this new renderer there, and I'm going to set the resolution on this just to something that will fit well in that square, and set the layout, or the width of the panel itself so that it matches. Now you've got a panel here where you can use the mouse to control the camera position and kind of move things around and view all of those points. Now I'm going to create another copy of this select here, move it over here with the point map renderer, and connect it to the second input. Now if you zoom in here, you can see that we've got some values in here now, and in this top row we've got that similar area of kind of blank pixels for the points that don't actually exist. If you turn on display pixel values, you can mouse around and look at the data that's in there. Now for all of these points, in the SDF data, all three channels are going to be the same, and what's in there is the distance of the nearest surface to that point in space. Now going back to this diagram here, if one pixel in that position's top has coordinates right there, then that distance is going to be that distance from the point there to the surface there. And if the coordinates are for that point there, it would be this distance here. So doing the same thing in the color data top here, these values are all still 0, and that's because we haven't set up a material for this yet. Now looking at these values again, you'll notice that some of them are negative, and what that means is that the point is actually inside one of the shapes. So positive values mean that distance outside, 0 means directly on the surface, and then negative values mean inside one of the shapes. Now while we don't have the color data set up yet, we can still use this SDF data to come up with some colors to show in our grid of points here. Going to move this over a little bit to the side here. While we don't yet have color data set up, we can still use the SDF data to come up with colors that we can provide to the second color input on the point render component. So we just connect that directly. Everything gets pretty dark, and if you look really closely, you can kind of see some patterns, but it's pretty hard to make out. And that's because the values in here are often negative, and they're generally very small values, which when you use those directly as colors isn't going to show up very well. What we want is to have color that is white on the inside of shapes and black outside of the shapes. To do that, I'm going to create a threshold top and insert that between SDF data and the renderer there. Now in the settings, we're going to change the RGB channel here just to red and keep the comparator at less, and then set this threshold all the way down to 0. So now when you look at the points, if you move this around, you can see that there is definitely a pattern in there, and it is moving to kind of match the shape down here. If you look at it from the side, you can see that it's kind of got these sort of a cross section of this shape down here. Now you can try adjusting the threshold parameter here, and what that does is expand and contract the surface of the shape. Now if you think about how that's working, the distance is going to be 0 at the surface, and then it'll be increasing as it gets further away. If you set this threshold to 0.1, then it is effectively treating the surface as though it was 0.1 further out than it actually is. Now you can also put this negative if you want to kind of shrink it down, but it's a little bit hard to see because the shape isn't super large. Now that we've got our basic render setup going here, where we're using this SDF data to control the color of these points, we can look at some other options for coming up with that point data. So we used first was just a SOP converted to a chop and then to a top, so that you get that data based on those points and that geometry there. Now another option for this is to use point cloud data. Now there is a point file in operator you can put in there, and if we move this down here, insert a switch, and then connect up this point file here, you can use that switch and change the geometry there. Now the default file that loads for this is just the shell of a hollow sphere, which isn't particularly interesting, but there is another file. If you open up that picker there is a banana point cloud. Now zooming in a little bit there, you can see that it's kind of, you can see that the pattern, but it's because the point cloud data is so much more dense than the box, then it kind of all just merges into these flat areas. Now there is a setting on this point render for point size, so you can set that down to lower values, and now that the size of the points are smaller, you can kind of see a little bit better that it is separate points and not just like a surface. So what we've got now is this shape here intersecting the points from this banana point cloud file. Now there are all kinds of other options for different ways that you could come up with points to feed into this. You could use a GPU particle simulation or more complicated SOP-based geometry. For this tutorial, we're just going to stick with these two types of point sources. Oh, you can switch back to the grid if you want, or just leave it at the banana. Now, while we are able to use the mouse in this panel and of the point render component that we pulled in from the palette to move the camera around in here, the Raymarch renderer is just kind of always from that front angle, which isn't particularly useful for visualizing how these two things relate to each other. So it would be really great if we could have this bottom one move the camera in the same way as this top source. So this is going to use a different type of camera. So right now this is just using the default camera that's built into the Raymarch operator. But if you create a linked camera and connect it to the camera input on the renderer, so it still doesn't have a camera to point at, so it's still using the default, but you can set this camera path to the path to a regular camera comp. And there's a couple of buttons here to help create one of those and link it up for you if you want. But what we want is to use the one that's already in the point renderer. So we're just going to open up the parameters on this. Going to go over to this. Move this over a little bit so we can see that better. And we're going to go inside this point renderer component and drag this camera onto that parameter. So you'll see it's the path to the camera within that component. So closing the parameters and going back out. Now when you move the camera around in here, the camera that the Raymarch renderer uses is synchronized to that. And this is a really useful approach if you want to be combining a traditional render setup and a Raymarch setup, which we'll cover in more detail in a later tutorial. But for now, it's just useful to be able to see the two from the same angle. So to recap, what we have is a scene using this SDF-based geometry, which is right now just using a torus and a mirror octant with a chop that is controlling the rotate axis here to give it that animation. And that is going into two different kinds of renderers here. There is the Raymarch renderer, which is giving us this preview there. And then there is a point map renderer. And feeding into that, we have this setup here that is coming up with a top filled with XYZ coordinates in each pixel. We're doing that right now with a point file, and we also used a SOP converted to a top. That is being fed into the second input on this point map renderer, the positions point map input, and we've got these two different outputs here. This first one here contains SDF data, which is just the distance to the nearest surface, and this other color one we aren't using yet. Now we're using a threshold on the SDF data, is set to 0, and is looking basically for distances that are negative. And negative distances mean that they are inside of a shape. We're using that as the color input on the point renderer here. And it is instancing a bunch of points to those positions from the top and using this to set their color. We're then using a linked camera to share the same camera between that point renderer here and what's used in this Raymarch renderer. So it's pointing at the camera that's inside of that point renderer component. Our scene is using the SDF data to come up with colors for the points. And we're doing that through a threshold top. There are a number of different techniques that you can use with tops to come up with color values based on that data. And if you are used to working with tops, that can be a really intuitive workflow. So experiment with that and see what you can come up with. But there are some limitations to that approach. For example, if you have two different shapes in the scene and you want them to have different colors, there's nothing in the SDF data that differentiates between those. When you are using an operator like a simple union or a combine to merge SDFs, the result is a single combined SDF. So what comes out of that point map renderer in the SDF data doesn't have any indication of which part came from which shape. So the alternative is to use a material. We're going to create a sampled point material. And this is a special material that works only for point map render. So if we insert that here between the mirror octant and this null that's connected to both the renderers, this Raymarch based renderer is going to go dark, and that's because this kind of material doesn't really work in that context. So what we're going to do is, instead of inserting it there, we're going to insert it between the null and the point map renderer, so it's only being applied to that renderer and not to the main one. Now we take a look at the point map render here. We've now got some pixels coming up in this color data. If we take a look at the parameters on here, you'll see that we've got this fill color setting, we've got an edge color option, and then some other settings. So we're now going to set the fill color to orange. And then take a look at the point map render. You can now see that in this color data here, there are a number of pixels that are that orange color, and then some that are dark. So if we connect that to the point map render instead of this threshold, we now have color data coming from that material. So it is now similar to what we had before, where it is basically filling the shape here with that color. And there are a few other options that we can use here. So there is this separate edge color. So if you set that to something like green, that you can easily differentiate from the fill color, you'll notice that it is, some of the pixels are showing up in the green and some are showing up in orange. It's a little bit hard to see with these points which is which, so we're going to go back to our point data, and we're going to switch back to the grid here. And if we remember from earlier, when we changed that source of points, we also adjusted the point size setting here so that they're a little bit larger. So I was increasing that up to, say, 2, and then zooming out a little bit here. You can now see that there is kind of this orange area with a green area around it. Now, adjusting the material settings, you can control the thickness of that. So if you put it down pretty low, you'll have mostly an orange shape with this kind of shell of green around it. Now, there is also a blending setting which smooths the transition between the fill and the edge, and between the edge and the outside area. This blending setting can be really important if you are working with LED pixel mapping to avoid situations where you have lights that are kind of blinking on and off as a shape kind of brushes up against their area but doesn't quite get far enough in. So the blending will kind of smooth out those transitions and gets you a much cleaner shape. So if you turn this all the way down, you can kind of see some of that like blinking pattern there as the shape kind of moves past things. So bumping that back up, it smooths out those transitions. So now that we have our material here, so what we have here would still be possible with tops if you wanted to do it in that approach, but we're now going to add a second shape so that we can show some of the capabilities of the materials that are not possible with top-based coloring. We're going to create another torus. Move that down here, and we're going to keep the axis on Y. Change the radius to 1. We're now going to add some animation to the translate Y parameter to get it moving up and down. I'm going to move these up a little bit and create an LFO chop. We're going to set the channel name on this to TY for translate Y. The frequency down to something like 0.05. And then add a null chop and drag this channel onto the translate Y. So we are also going to create another sample point material here for this shape. And for this one, we're going to turn off edge, and we're going to change the color to something like blue that you can easily differentiate from the other colors that you're using. And we want to combine those two shapes. So easiest way to do that is with a simple union. Now we're going to connect both of these materials to it. And we're going to move things back a little bit here so we have a little bit more room. Now, if we were to just directly connect this to the Raymarch renderer, you would get that same issue with that material, that type of material not being supported. So instead, we're going to have another simple union, and then this one is going to be connected directly to those source shapes, so skipping over those materials. So we move that up there. We've got this other one here. And we can connect that to the Raymarch renderer, so you now see those two different shapes there. And then connect this first simple union up to the point map renderer. So zooming out here, now see that you've got this separate blue ring that's moving up and down, combined with that other pattern using that green and orange material. To recap, we are using two different SDFs. We're applying a little bit of animation to each of them. We're applying a different sample point material to each one, combining that with a simple union and feeding it into this point map renderer. We're then using another simple union, combining those two shapes but without the materials, and feeding it into the Raymarch renderer, which we're using for this preview panel here. Then using a grid of points from a SOP, converted into a top of coordinates, fed into the point map renderer, which is then being passed into, which is then producing this color data, which is being passed into this point renderer component from the touch designer palette, and it's using that to control the color.